Quantum communication is already known to allow us to solve many other problems in a better way. And I shall briefly give you a few more examples. Quantum communication has also shown to be very useful to solve other cryptographic problems. For example, the problem of secure identification. Where I have a password, a remote server has a password, and we want to compare whether the password is the same in order to identify myself. Quantum communication can solve this problem, in fact, where the end nodes are only required to prepare and measure single qubits. And it can do so in such a way that security is retained even if large quantum computers come online in the future. Another cryptographic application is called position verification, where quantum has shown some advantages. Position verification means that we want to determine where someone else is actually located. If you phone with your friend who says, "I've made a trip to China," but they're actually next door, you want to be able to find that out. So this task is known as position verification. And again, quantum has shown significant advantages in this domain. And again, it is sufficient for the end nodes to prepare and measure only single qubits. Quantum communication is actually useful for many other cryptographic tasks. And the intuition here is that we can use quantum communication to build up correlations in a network which cannot otherwise be generated. And then we do some classical communication at the end in order to process these correlations to solve useful tasks. Quantum communication has also been shown to be very useful to perform clock synchronization. So here we want to know how to align clocks which are far apart. Quantum communication has also been shown to be quite useful for sensing. For example, to sense differences in the magnetic field on Earth. And finally, quantum communication has also shown to be useful to enhance the baseline of telescopes. So what is the intuition here? People have combined telescopes, for example 2 of them, in order to get a better picture of the sky. Now the input to these telescopes, what they observe, is light, photons coming into the telescope. Now the way that 2 telescopes can be combined is by performing an interference experiment combining the light of the 2 telescopes. Roughly speaking, now if 2 telescopes are very far apart, then entanglement between these 2 telescopes actually allows us to teleport the state of a photon from one telescope to one which is very far away, and then perform an interference experiment, thereby extending the baseline of telescopes. Quantum communication has also been shown to, for example, help players in games. For example, playing bridge. 2 bridge players can coordinate better using entanglement than they can using just a classical strategy agreed ahead of time. And this helps them to gain an advantage in winning the game. All of these effects are due to 2 properties of entanglement, namely maximum coordination, allowing us to solve synchronization, coordination, and agreement tasks more efficiently, and the second one, namely that entanglement is inherently private, giving entirely new features to security and privacy.